Okay, we are going to start now. Hello, good afternoon, everyone. Welcome to this webinar, ASME Section 8, Design of Pressure Vessels. This webinar will cover the essential aspects of the design and manufacture of pressure vessels for industrial applications. This webinar will be presented by Javier Tirenti. Javier is a senior mechanical engineer. He has more than 20 years of experience in the design, calculation, and fabrication of pressure vessels, heat exchangers, storage tanks, piping systems, and structures in general. Javier is an ASME authorized instructor. He has an extensive experience providing specific training sessions in both classroom and online modalities. He is the director of Urban Training and Engineering, as well as the director of the Master of the Mechanical Equipment Engineering for Industrial Plants. Good afternoon, Javier, and welcome.
Thank you so much, Lucia, for this very nice introduction.
Thank you. So I think that you can start.
Fantastic.
It's all
So now
yours.
the responsibility is all on me. Thank you so
Yes.
much for this introduction. Good afternoon, everybody. It is my pleasure to be here this afternoon discussing with you about this very interesting topic that are pressure vessels. And we have, let's say, a very ambitious goal ahead of us, because to talk about pressure vessels in 45 minutes, 1 hour, or give or take, it is ambitious. We could be speaking about pressure vessels for 6 months, and yet we wouldn't be able to decipher one of the basic things of the ASME code. But today we are not here to talk about how difficult this is, but to try to put out there basics and, let's say, essentials and fundamentals about this topic. So without further ado, let's get started. When it comes to pressure vessels, there are some questions that are essential, as I was saying before, and that they need to be discussed. And why not start with a very typical question, that is, which are the most commonly used design codes in pressure vessels? Well, there are several design codes, as you all know. One of them, being probably the most used, is the ASME Section 8 Division 1 and 2. Here it says USA and North America, but the ASME Section 8 code is used worldwide. It was originated in the USA or North America, but we all know that it is applied worldwide. But then again, there are some other design codes, as the EN 13445, that is applicable in the European Union, or the AD Merkblad code applicable in Germany, or the British code PD 1500s applicable in the UK, or CODAP, JB 150, so on and so forth. So there are several different pressure vessel codes. It all comes down to which one is applicable to our project. So if you are participating in the oil and gas sector, it is very likely that the ASME Section 8 Division 1 or 2 code is going to be applicable in your field. So it is very good to have a good understanding of this design code. But it is also important to understand that besides a design code, it is also important to know that there are some other requirements, and not only requirements from the design point of view, but it could be a requirement from the legal point of view, legal perspective, in terms of legislation. For example, off the top of my head, all pressure vessels that need to be installed in the European Union, they need to comply with the CE mark, for example. It is a stamp that pressure vessels need to include when they are to be installed in the European Union. Likewise, if the pressure vessel needs to be installed in the USA or in North America, sorry, by law, the pressure vessel needs to be stamped by ASME or ASME. So those requirements need to be taken into consideration, as well as customer requirements or job specification requirements. When we are participating in a project, there are specifications that we need to comply with, as you all very well know. And those specifications, in many occasions, are more stringent than the ASME code itself. So this is a very good point to be evaluated and considered before the design is started. Let's move on to what committees or working groups does the ASME have? Well, the ASME has many committees, more than 100 probably. And when I say committees or working groups, I am referring to a group of people developing and studying a specific, let's say, code for a specific field. For example, one of the most committees that one of the, let's say, most well-known committees in the oil and gas business, in order to cite an example, one of them is the Boilers and Pressure Vessel Code, in which the section 8 is included, that we are discussing here today. And on the other hand, we have the B31 Piping Systems Code. So here we have two committees. Both of them are very closely related. On the left hand side of the presentation, we are seeing the Boilers and Pressure Vessel Code, pressure vessels, shell and tube heat exchangers, etc., etc. And on the right hand side of the screen, we have the B31 piping systems. Both committees deal with equipment under pressure, but the rules are not the same between the two committees. So one of the first things we have to understand when it comes to designing a system or an equipment is which committee or which code we have to follow in order to develop our design. Another question, very interesting question to answer, it is to understand the organization of the ASME Boilers and Pressure Vessel Code. The Boilers and Pressure Vessels Code is divided in different sections. Each section covers a specific field, and a specific field within the Boilers and Pressure Vessels Code. For example, Section 1 is going to cover power boilers, Section 2, materials, Section 5, non-destructive examination, Section 8, pressure vessels. So there are different sections within the Boilers and Pressure Vessel Code. Some of the sections, for example, like Section 8, pressure vessels, are design codes for specific type of equipment, pressure vessels in this case. But there are some other sections, like, for example, Section 2, materials. This section, it is going to provide, is going to indicate all requirements for the design sections. design and fabrication sections. For example, if we are designing a pressure vessel and we need to we need to establish the mechanical properties of the materials we need to fabricate the pressure vessels with, we are going to have to check section 2 of the boilers and pressure vessels code in order to get the right mechanical properties of all those materials that we are working with. That is why it is very interesting to understand this this committee, this working group, the boilers and pressure vessel code as a whole, and also to take into account that some of the requirements, and some sections are common for different design codes. That is the case of section 2, section 5, non-destructive examination, section 9, for example, welding and bracing qualifications. When it comes to design of pressure vessels, we are going to be dealing with we're going to be dealing with section 2, section 5, and section 9 on top of section 8, that is pressure vessels. The code is edited every 2 years in July, and it is not mandatory until the next January of the following year. So let's say that the latest edition of the ASME Section 8 code, it was in 2021, in July 2021. So it was not mandatory until January 2022. Next edition, it is going to be July 2023. But anyway, how is the ASME Section 8 code organized? Well, let's start by saying that it is divided into 3 sections or divisions. In this case, division 1, 2, and 3. And let's start with division 1. Division 1, it is a division of the Section 8 code that contains different rules for the design of pressure vessels. So division 1, it is known as DBR, Design by Rules Code. There are certain stress theories included in this division. And since we are talking about design by rules, that means that there are certain design factors included in the different equations. And we could say that due to these design factors, the design that we're going to obtain with division 1 is conservative in comparison with division 2 and division 3, of course. There are some, let's say, boundary conditions and limitations of this division. Vessels up to 210 bars and pressures higher than and also we need to take into account that this division is applicable to pressures higher than 1 bar, 1 atm, or 15 psis. And why is that? Well, all design codes, they do have rules and limitations and boundary conditions in order to limit the application of that division in this case. If we evaluate division 2, it also contains rules, but at the same time, we are going to find different procedures and analysis for the design of pressure vessels. For example, like the analysis methodology for fatigue analysis. Fatigue analysis requires a methodology that needs to be used when it comes to determining the different peak stresses, for example, or those areas of the pressure vessel that could be subjected to fatigue. That is why in that division we find some rules, but at the same time analysis methodology in terms of fatigue, for example, and some other scenarios. It is a more stringent design code. The evaluation of stresses is more detailed than the one performed in Division 1. And that detailed evaluation of stresses allows us to work with higher allowable stresses in comparison to Division 1. We are going to touch on this a little bit further on the presentation. And then we find Division 3. Division 3, it is dedicated to vessels under very high internal pressure, for example, up to 700 bars and above. This is not a very typical case in normal industries or fields that we could be working on. For example, nuclear facilities, they do reach higher pressures as far as or close to 700 bars in some cases, but at the same time there is a complete section dedicated to nuclear facilities. So within the ASME boilers and pressure vessels code. So Division 3, it is not as much applied or used as Division 1 and Division 2. But anyway, the question could be when to use Division 1 and when to use Division 2. Well, the answer is it depends. There is no straight answer to that one, to this question. There is no, we cannot draw a line and group Division 1 pressure vessels and Division 2 pressure vessels. Each case is different. So since each case is different, we need to perform an evaluation and try to identify which pressure vessel is more suitable for a particular set of rules or which pressure vessels are suitable for analysis. That would be Division 1 and Division 2. Let's say that sometimes when I am in the classroom, there are some questions that are always difficult to answer and that could corner the instructor and it could be challenging to draw a line. Well, this could be one of those questions. When do I know that I have to apply Division 1 or Division 2? As I said, it's not easy way. There is no easy way about it, but let's simplify it. If we need to fabricate or design a pressure vessel up to 20, 30 millimeters in thickness of the shell, it is very likely we are talking about carbon steel, no corrosive, a very corrosive environment, so on and so forth. It is very likely that that pressure vessel is going to fall into Division 1. However, if we are we have a pressure vessel with, I don't know, 150 bars of internal pressure and under cyclic conditions that could lead into fatigue in the pressure vessel, and we do need to perform a fatigue analysis, that pressure vessel, it is very likely that it's going to be Division 2. There are several charts and graphs that try to divide or categorize pressure vessels into Division 1 or Division 2, but this is not very easy and it is not very straightforward. So I wouldn't recommend trying to categorize pressure vessels in Division 1 or Division 2 beforehand. This is always a technical, economical decision that we need to carry on with these pressure vessels. So, but what is the scope? What is the scope of the ASME Section 8 Division 1 code? And in terms of scope, I am referring to, can we design any container subjected to internal pressure vessel? And the answer is no. Not every container subjected to internal or external pressure can be designed under the rules of Section 8, Division 1. And why is that? Because there are different boundary conditions that need to be taken into account. And since it is very, very difficult to list all the type of equipment that could fall into the category of Section 8, Division 1, the committee, in this case, has decided to list all the items or types of equipment that are not included in the scope of Section 8, Division 1. For example, a boiler, a power boiler like the one we are seeing on the screen. So a boiler cannot be designed or fabricated under or according to ASME Section 8 Division 1. And why not? Because there is one specific section within the Boilers and Pressure Vessel Code, that is Section 1, that is entirely dedicated to power boilers. So if there is a section within the Boilers and Pressure Vessels Code that is dedicated to that type of equipment, we cannot design it or fabricate it following the ASME Section 8 Division 1. That is one of the type of exceptions that we are going to find within the ASME Section 8 Division 1 code. Same as for process tubular heaters. The direct fire happens the same, or rotating equipment. Rotating equipment, they do have components or compartments that are under internal pressure, like the pressure chamber in a centrifugal pump. However, it is very clearly stated that parts or components of rotating equipment cannot be designed under ASME Section 8 Division 1 code. So prior to any development and prior to any, let's say, pre-design, we need to make sure that we are in the right spot in terms of scope for the equipment that we have on the table. Piping systems. Piping systems are excluded from the scope of Section 8 Division 1. In some cases, it is very difficult to differentiate a piping system from a pressure vessel. For example, item pipes that are installed in line of a piping system. Well, those items are difficult to differentiate and to establish which code it is to be applied there. However, that evaluation needs to be performed. And also, there are some limitations in terms of geometry and dimensions of a pressure vessel. If we have a pressure vessel as small as the one we are seeing on the screen, in this case, a shell and tube heat exchanger, that pressure vessel or this equipment cannot be designed and manufactured as per ASME Section 8 Division 1. The limitation is dimensions smaller than 6 inches or 152 mils from either internal diameter, width, height, or diagonal. So if our pressure vessel it is under those limits, we cannot design it or manufacture it as per Division 1 rules. Or pressure vessels for human occupation. These pressure vessels are different than the ones we are fabricating for the oil and gas sector, for example. So in that case, these type of vessels also fall into the exceptions list. And we also need to take into account that the ASME code Section 8 Division 1 has scope limits. Not every single rule and not every single design alternative is going to be contained in this division. That is why if we check if we check section U2, section G, paragraph G, we are going to see this beautiful paragraph that indicates this division of section 8 does not contain rules to cover all details of construction. It means that if we need a special design that is not common enough in order to be included within the limits of within the scope of ASME Section 8 Division 1, we are going to have to take another road, another evaluation road. For example, finite element analysis. That is a very well-known methodology these days, and it is being used more and more in order to complement the evaluations that we could perform in a pressure vessel for let's say standard components and standard loading conditions. As you can see, we are starting from general to specific. We have started discussing the boilers and pressure vessels code, and we continued with section 8, and now we are going to continue with division 1. So how is division 1 organized? Well, the organization of section 8 division 1, it is the following. We have mainly 3 subsections: subsection A, subsection B, and subsection C. Subsection 8 covers general requirements, and that is why we are going to find within subsection A, we are going to find part UG. Part UG stands for unfired and general, because Section 8 Division 1 covers unfired pressure vessels, and since unfired, it is a very specific and important division within a pressurized equipment. We are going to, throughout Division 1, we are going to find the letter U. It comes from unfired. So part UG stands for unfired and general. Then we move to subsection B, where we are going to find all the fabrication requirements. Fabrication requirements that cover different fabrication techniques, such as welding, UW, forging, section UF, forging, and section UB, bracing. Within these different parts, we're going to find the requirements for the different fabrication techniques that could be used in the fabrication of a pressure vessel, of course. And then we move to subsection C, where we are going to find all the material requirements for the different materials that are going to be used in order to manufacture a pressure vessel, to design and manufacture a pressure vessel under internal or external pressure, among other loading conditions, of course. So within subsection C, we're going to find different parts. Part UCS, that stands for U, unfired, as we mentioned before, and CS, carbon steel. Then if we have to use non-ferrous materials, we need to understand and comply with all the requirements for non-ferrous materials, or high alloy, cast iron, cladded vessels, or high temperature or layered welded pressure vessels, so on and so forth. And at the same time, we are going to find 48 mandatory appendices, and we're going to find several non-mandatory appendices from A to PP. These appendices are very useful indeed, not only mandatory ones, but non-mandatory ones. So the code does not end in the main body of the code, but also appendices need to be taken into very serious consideration and need to be complied with in the case of mandatory appendices. As you can see, these parts that we're going to be dealing with are somewhat, let's say, a little bit difficult to comprehend or difficult to find, let's say. That is why there are out there, there is a term that I like to use, that is we are intoxicated. We are intoxicated of information. We are intoxicated with information these days. So the difficult part, or one of the most difficult jobs of an engineer, in this case, it is to decipher which is the good information of the, let's say, of all the rest. So in this case, it's the same, how to decipher which parts of the code are interesting for me or for the project that I am developing. Well, there are some, let's say, diagrams like the ones we are seeing on the screen right now, where if we take a little portion of that diagram, we can see that, let's say that we need to design an ellipsoidal head. And for the design of the ellipsoidal head, we need to comply with different parts of the ASME Section 8 Division 1 code. So this shortcut is indicating us which part and which paragraph of Section 8 Division 1 we need to check in order to make sure that the main aspects of that ellipsoidal head are taken care of or are considered. In this case, for example, this shortcut is indicating that we need to comply with UG32D, which indicates the thickness calculation, minimum thickness requirement for heads, in this case under internal pressure, or we are going to need to comply with UCS 79, or we are going to need to comply with Appendix L for joint efficiency diagrams, for example. That is just a brief overview of these shortcuts, how they operate, but it could be for a beginner, it could be a good idea to have, let's say, an overall picture of Section 8 Division 1, where to look in terms of making sure that the main requirements of Section 8 Division 1 are covered. And leaving aside Section 8 Division 1, the scope and the organization for a moment, and moving into the loading cases of pressure vessels, it is worth mentioning which loads are applied or could be applied in a pressure vessel. Not all loads that we're going to be describing or mentioning right now are necessarily applied in a pressure vessel, but these are the main ones that are worth considering when we are in front of a design of a pressure vessel. So first of all, temperature. This is it comes naturally for designers and engineers to think about temperature when it comes to the design of this type of equipment. But we also need to take into account that the temperature that we need to consider could be a very high temperature if the process requires it, or it could be cryogenic temperature if we are working on, I don't know, an LNG plant, for example, and the different extremes, high temperature or very low temperature, they do have a different impact on the materials that we are working with. So the different stages or the different batches of temperature within a process need to be considered when we are dealing with the design. Maybe the process works or operates 12 hours, half day at 258 Celsius degrees. And the remaining 12 hours of the day, the rest of the day, it works at 438 Celsius degrees. We need to combine those temperatures with the coinciding pressures at those temperatures in order to understand which design condition is more stringent for the pressure vessel that we are dealing with. Another design condition that we need to consider is the pressure. The pressure could be internal pressure, external pressure, and also we need to understand how to evaluate the maximum allowable working pressure of the pressure vessel, of course. Weight, leave loads, dead loads, cyclic loads. There are different loadings that could be applied into different components of a pressure vessel. Could be the nozzle, could be the saddles, could be, you name it. There are several different type of loads that could be applied, that could be, yes, applied into a pressure vessel. So all of them need to be considered. At the same time, the liquid height in a pressure vessel could impose a very demanding situation for large diameter cylindrical pressure vessels supported into saddles, for example. So in some pressure vessels, the stored liquid is going to be negligible, and in some other pressure vessels, the stored liquid is going to be the governing case. Let's assume a 10-meter diameter cylindrical horizontal pressure vessel that is subjected to 3 bars internal pressure. The thickness of the shell is going to be very thin due to the low requirement of internal pressure. But then again, if this huge diameter or large diameter cylindrical pressure vessel, horizontal cylindrical pressure vessel, it contains, I don't know, 8 meters height liquid, could be gasoline, could be water, could be whatever liquid, that is going to impose heavy stresses on the saddles of that vessel. That is why it's going to be very difficult to design that area, and we are going to face a huge stress concentration in that area. So what I'm trying to say here is that we need to evaluate all design conditions beforehand, because we could be surprised of the effects of all these conditions. External conditions, wind, seismic, snow conditions, all these are external conditions applied to the pressure vessel that on many occasions they are governing the design of the pressure vessel due to the loads that are imposed for these external actions. So that is also, those actions are worth considering at the very beginning of the project. And yet it is a little bit ironic, but it is more and more often due to fast track projects and the hassle that all engineers are dragged into with these projects. Due to the hassle that we are forced to work with, we are going to have to start designing without all the design conditions properly fixed. So we are facing more and more challenges in terms of changes in design conditions. And that is very difficult to cope with, especially with the tight deadlines that we handle in the projects now, in the different projects nowadays, of course. Okay, conditions such as steam out or hydrostatic test or transportation. In some cases, transportation conditions are going to be governing the design of a pressure vessel. Believe it or not, this happens, and it is very dangerous because if you do not take into account transportation's loadings at the very beginning of the project, and if you do not use the right approach and the right transportation conditions, it is very likely that the design is not going to be adequate. And once you try to incorporate or include the loadings for transportation or lifting into the evaluation, that vessel is going to fail, and you're going to find yourself in a situation where you're going to have to start redesigning the pressure vessel. And if the manufacturing process is already ongoing, that is not a nice spot to be at. So take that into account. Joint efficiency. Let's move towards joint efficiency. What is the joint efficiency of a pressure vessel? Well, the concept, or let's say the definition, is very straightforward. To really understand it, it is a little bit more complex, but the joint efficiency of a welded seam is the reliability level that can be obtained from that welded joint or welded seam. There is no more than that. The question is how to obtain the joint efficiency, but prior to that, the question is what is the joint efficiency be depending on? So it depends primarily, it depends on the NDE level, the NDE tests that we apply in a pressure vessel. The non-destructive examination level that we applied in a pressure vessel is going to be responsible for the most part of the joint efficiency value that we are going to be using in the different design calculations performed for a pressure vessel. So on the one hand, we have non-destructive examination, and on the other hand, we have joint category and type. A better joint type and preparation, of course, is going to mean a better joint efficiency. So we need to understand that there are different categories within a pressure vessel. For example, the longitudinal weld joint in the cylinder is the most important weld within a pressure vessel. Why? Because of the stresses that are going to be induced, the stress distribution that is going to be applied in the shell of a pressure vessel. The longitudinal seam, it is going to be the most demanded or affected due to the stress distribution. In that regard, the category of this welded joint is A. It is the most important of all the welded seams in a pressure vessel. Then we can find in circumferential welded joints, we can find category B. Then we're going to find category C, for example, in the joint of flatheads with the cylinders in nozzles, so on and so forth. And besides the category of the welded seam in a pressure vessel, we can choose from different joint types. And these joint types are going to be indicating, or the different joint types that we can use in the fabrication of a pressure vessel. Depending on the joint type, we're going to obtain one joint efficiency or another. That is also something to take into account. And then we need to understand that there are different levels of radiographic test in a pressure vessel. The ASME code defines different levels of RT. We can find requirements, or we can find applications where we're going to need to apply full RT in a pressure vessel. There are some other applications that are not so stringent in terms of NDEs, and a spot RT could be applied, random RT could be applied to evaluate the different welded seams and joints in the pressure vessel. And there are some other applications where the designer or manufacturer is entitled to choose whether to apply an RT level or not. That is a decision up to designer, manufacturer, or let's say owner, operator, ultimately, that it is the responsible for the pressure vessel. The joint efficiency is somewhat cumbersome to understand, and it is, let's say, one of the most difficult areas within the design requirements of a pressure vessel. But in simple terms, if we increase the level of non-destructive examination in a pressure vessel, the reliability of the welded joints increases, and that is why the thickness of the components is going to decrease, because the reliability is high. On the other hand, if we decide not to apply non-destructive examination, RT, if we do not wish to, in those cases where we can allow, where we can choose the path of no RT, if we decide not to apply RT or to decrease the level of the NDEs, the reliability of the welded joint is going to decrease at the same time. And the thickness required for the components is going to increase. So there are some pressure vessels where the requirements of non-destructive examination and joint efficiencies to be used are very clear due to the contents stored in the pressure vessel or due to other requirements. There are some pressure vessels where the joint efficiency values to be used are crystal clear, but there are some other areas where it is up to the owner, designer, manufacturer to decide whether to use one level of one joint efficiency value or another joint efficiency value. In those cases, it is just a matter of a technical economical evaluation. For all that we've been discussing in this part of joint efficiency, the more NDE applied to a pressure vessel, the lesser thickness required. The less NDE level applied in a pressure vessel, the higher thicknesses that are going to be required. So this is a selection that is going to be based on cost and material availability only. There are some cases where it is not, there is no a straight line that divides one possibility of joint efficiency or another. And in order to, let's say, round up the presentation, let's talk about a little bit thicknesses, required thicknesses for pressure vessels under internal and external pressure. And well, under internal pressure, we can all understand that depending on the shape of the pressure vessel, whether it is spherical or cylindrical, the stress distribution is going to be different. We can see it in the whole geometry of these two types of pressure vessels, or we can evaluate different we can evaluate a very small element within the pressure vessel. We are going to see that the stress distribution and the type of stresses induced in these two types of elements in a spherical vessel or cylindrical vessel are going to be different. And these two and this differentiation within the distribution of stresses is going to yield a different approach for the required thickness of a pressure vessel under internal pressure. If we move towards the equations of the ASME Section 8 Division 1 code, paragraph UG 27C1 and 2, we're going to find two equations that directly relate the thickness, the required thickness for hoop stress or circumferential stress, and thickness for longitudinal stress in this case. They directly relate the thickness required with the internal pressure and the internal radius of the pressure vessel. So in other words, the thickness is going to be directly proportional to the internal pressure and directly proportional to the internal radius of the pressure vessel. And at the same time, the thickness is going to be inversely proportional to the allowable stress of the material, the mechanical properties of the material. So the better material we use, the less thickness that is required. The higher the pressure, the higher the thickness. The higher the diameter, the higher the thickness. And that is the relationship we need to take into account. And the last element that we are going to see here in the equation for internal pressure is the joint efficiency. The joint efficiency, the better knowledge and the better reliability that we have on where the joints, the higher would be the joint efficiency and the lesser would be the thickness required for that pressure vessel. So the approach is very straightforward in terms of the rule for the thickness of pressure vessels under internal pressure. But what about external pressure? Is it possible? First of all, let's answer this question. Is it possible that a pressure vessel is subjected to external pressure? Well, let's see. This is a test case. This is an induced failure of a pressure vessel in order to demonstrate the effects of an external load applied to a pressure vessel. So as we can see here in this demonstration that was done on purpose on this pressure vessel to show you, to understand the collapse that a pressure vessel under external pressure suffers. In this case, we can see that the failure mode of a pressure vessel under external pressure, it has nothing to do, it is just the opposite of the failure mechanism of a pressure vessel under internal pressure. In this case, when a pressure vessel is subjected to external pressure, what we can see here on the screen is that the equipment collapses because it can no longer sustain the loads applied. And which loads are applied in this case? Well, in this demonstration, we can see that a vacuum was created inside the pressure vessel. And since there is vacuum inside the pressure vessel, the external load applied is the atmosphere. 15 psi's are applied to the cylinder. And the question could be, well, it is a little bit strange that only 15 psi's are going to be damaging this pressure vessel in such a catastrophic way. Yes, it could be it could be difficult to understand at first, but this is the result, because it is all about moment of inertia. And how are we going to be evaluating all these scenarios, and which could be the causes of external pressure applied in a pressure vessel? Well, it could be steam out. Let's say that we are cleaning a pressure vessel with steam. The pressure vessel is pressurized, and all of a sudden the temperature drops considerably on the shell of the pressure vessel, and this temperature drop is going to produce condensation of the steam. That condensation, it is going to bring a drastic drop in pressure as well, and that drastic drop in pressure could lead into vacuum inside the pressure vessel, and that is why external loads could be applied. Or a jacketed vessel, submerged, undersea pressure vessel. There are different occasions where a pressure vessel could be subjected to external pressure. The calculation for pressure vessels subjected to external pressure, it is a little bit tedious because it is a verification process. In other words, we need to define all the components and geometry of a pressure vessel. And once the geometry and the components are defined, we need to obtain the equivalent moment of inertia that is applied, or let's say that it is available in the pressure vessel. And later on, with that moment of inertia, the allowable external pressure of the pressure vessel is obtained and then compared to the required external pressure applied in that particular case. For that procedure, we need to use different tables, and the variables involved in this calculation are going to be the diameter, length, thickness, material, and the stiff points of the pressure vessel. As I was saying before, we need to use different tables, and with all these parameters, we're going to be able to compare the allowable external pressure of the pressure vessel and compare it with the external pressure vessel load that is acting on the equipment, and determine whether the pressure vessel is able to withstand the external loads or not. And one way of counteracting the external loads are stiffening rings. That is why when you see a vessel with these elements here, these elements are stiffening rings, and those components have the mission of stiffening the shell. That is the component that in a cylindrical vessel is going to fail first, and in that case, those stiffening rings are going to be adding inertia to the geometry of the pressure vessel, and the construction, it is going to be more robust in order to counteract the external loads of the pressure vessel. Okay, everybody, up to here, we wanted to cover the basics and the essentials of pressure vessels. Obviously, that in an hour, it is very difficult to cover such extensive subject like the ASME Section 8 Division 1, but this overview, I am sure, is going to be suitable and is going to be beneficial for some people. And now I am more than happy to answer any questions that you may have related to what we've seen or any other questions.
Thank you, Javier. Now we have, as Javier mentioned it, a few minutes to answer questions. So don't be shy and raise your hands on, or you can write the questions in the chat. I do have one question, Javier.
Okay.
If the design code is not specified in the project, which one should I use?
Very good question. And we are not starting with a simple one, Lucia.
I want to make your life more complicated.
You want to make my
Yes.
life a little bit more complicated. Okay. Let me tell you, it is not necessary, but anyway. Well, first and foremost, we need to indicate that the designer is not responsible for defining the code to be applied in a particular design or fabrication. It is the owner of the pressure vessel, the responsible one to define this. And why am I saying that? Because in some cases, it's very straightforward which code needs to be applied, in the case of North America, for example. But there are some other regions in the world where it is not so natural to define one code or the other. Within the selection of the design code, there are different decisions that need to be made, such as the design factors included, the risk evaluation of the pressure vessel, the fees of the insurances that are going to be paid. There are many factors involved. So the first thing would be to ask the owner, and if there is no clue about it, the exercise of looking to both sides and understanding the requirements of another similar industrial plants than the one that we are working on, which requirements they are using, and try to emulate and start the I don't know, the questions from there. Which codes are being used in some other industrial plants, in order for me to have a baseline and take it from there.
Okay, thank you very much for your answer.
You're very welcome.
We have one question in the chat.
Okay.
It's from Emmanuel.
Okay.
And the question is, does the building or position the pressure vessel is kept or used affect the working pressure or external pressure acting on the pressure vessel?
Very good question, Emmanuel. Thank you so much for this. The short answer is no. The short answer is no, or the short answer would be it doesn't necessarily have. It doesn't have to affect the pressure vessel in terms of external pressure. External pressure, we need to understand it and consider it as the same pressure applied to every single point of a pressure vessel. So external pressure is when we submerged a pressure vessel under sea, for example. But if the pressure vessel is on a structure, for example, and there are some components of the structure that are transferring loads to the pressure vessel, that is not external pressure, but it needs to be considered, because those could be external loads applied to the pressure vessel, and those could be local loads that could be inducing stresses in the shell or any other component for that matter. So those type of loads are not considered as external pressure loads, but they could be, or they are considered as local loads applied on the external part of the component and needed to be evaluated. Could be WRC 297, WRC 537. We could use several approaches to evaluate those loads.
Okay.
I can see that Cesar has another question that he's posting another question in the chat.
Okay, we can wait.
Yep. Or you can,
Or
I don't know if there are any other questions.
yeah, in the meantime, I have another question that we received by email,
Okay.
sorry. And it's when should we design as per ASME VIII Division 1 and when as per ASME Division 2?
Very good question. As we extensively commented on this throughout the presentation, unfortunately, there is no thin line that is going to divide these two areas. When to use Division 1 and when to use Division 2. As I said before, if we need to start by saying or drawing a line, probably we can relate it to the level of internal pressure, or we can relate it to the thickness of the shell. But each case is different, and there is no easy way around it, unfortunately. So 20, 30 mils carbon steel pressure vessels are very likely to be Division 1, and high pressure vessels, for example, are very likely to be designed and manufactured as per Division 2. But other than that, I know that the answer is very vague. I apologize for that, but there is no easy way around it.
Thank you anyway. Now we have another question
Okay.
from Cesar. Sorry, 1 second. Is designing a vessel or a tank using a mixing agitator is covered in this standard? Because I think API 650 covers only storage tanks, but not with an agitator.
Very good question, Cesar. I hope I am pronouncing your name adequately, same as in the case of Emmanuel. It is a very good question. Yes, this is covered. This is covered within the ASME Section 8 Division 1 code. Actually, if you go to the code and you search for the word mixing or agitator, I am not 100% sure that you're going to find it, but you don't need to find agitator, because UG16 and UG20, they do include different loaded conditions, and actually these paragraphs clearly state that you need to consider all types of loads applied in the different parts and components of a pressure vessel. The agitator is going to be is going to be applying and transferring a torque and probably axial and transversal loads in the nozzle that they are going to induce a load and a stress scenario, obviously. So they do need to be considered. For example, they could be evaluated as per WRC 537 or 297, as I was saying before. And as you very well said, Cesar, API 650 does not cover specifically the case of agitators, but even though you are designing a a storage tank in that case, as per API 650, you can evaluate the stress level induced in a nozzle due to an edge agitator, as well with WRC, as I said before, 537 or 297. It is possible. You're very
Okay.
welcome, Cesar. I am happy that it's very clear. Also, Emmanuel, thank you. I am pleased that I answered your question.
Okay, we have another question from Okan. What are the critical points about designing a spherical storage tank? Is there a guideline book? Thanks in advance.
Thank you so much, Okan. Very good question. The most or the critical part when it comes to designing a spherical storage tank or a sphere would be the structural part and the intersection between the spherical part and the legs itself. Normally, spherical tanks or spherical pressure vessels are designed with legs. Normally, it is not 100% of the cases, but it is very typical. And the stresses created around the joint between the sphere and the legs, it is under a lot of stress concentration. So that area needs to be evaluated with detail or in detail. And nowadays, that evaluation is performed with following the rules of Section 8, Division 1. For example, could be some spheres are designed as per Division 1. Some others are designed as per Division 2, which is also very frequent. But in any case, the area between the shell itself and the structural parts of the sphere are further evaluated by means of finite element analysis. Nowadays, we can also question, we can always wonder, okay, but what happened 30 years ago when finite element analysis was not available? Well, 30 years ago, designs were more conservative and some other, let's say, checkpoints were also used for that area. And apart from finite element analysis, I would recommend as a guideline, as a starting point guideline, I would recommend the Pressure Vessels Design Manual by Dennis Moss. If you type Dennis Moss directly in Google, you're going to find the Pressure Vessel Design Manual. It is the best starting point in order to learn how to properly design the legs of or a spherical pressure vessel. Thank you very much, Okan. Very good question.
Thank you, Javier. I don't know if anyone has another question. If not, I think that we can finish here.
Okay.
Thank you, says Okan. I think someone is typing a question.
Yeah,
So we
typing a
can
question or saying goodbye.
or saying goodbye.
Could be.
No, thanks a lot. He's saying goodbye. So
Okay.
I would like to remind you all that this webinar has been recorded and that from tomorrow it will be available on our YouTube channel for anyone who wants to watch it again or who couldn't attend. If you enjoyed this webinar and want to learn more about this topic, we remind you that the week of October the 3rd, we will be teaching this course via Microsoft Teams, and that you also have this course available in its self-guided version. And that's it. Thank you all for being with us this afternoon, and thank you, Javier, for this interesting webinar.
Thank you so much. Gracias, William. It has been truly a pleasure for me to share this time with you, with everybody. So I hope to see you soon. And whatever you need, you already know where to find us. Thank you so much and have a good day.
Thank you. Have a good day. Bye
Thank
bye.
you. Thank you. Bye bye. Thank you.